Welcome back. In the second part of today's course session, we are going to roughly wind up our discussion of expectation of random variables. We've already computed this weighted averages of the values of random variables in several specific scenarios. We've seen the formula, and we put it to good use to calculate the expected number of heads that we get when we toss a fair coin twice or 3 times. And we saw that there is some kind of connection between these two quantities. We'll see that this connection is not there by chance, but actually there are 2 important properties of expectation that explain it, and also that can be used to simplify our calculations for expectation, the values of expectation in many scenarios. Before we do that, let me consider, by way of warm-up, another calculation of expectation, a specific one, that has to do with the value of a random variable that is related to coin tosses. So suppose I'm interested in the expected number of tosses that I need to see I need to perform before I get ahead. So if I get ahead straight away, then the value of the random variable for that experiment would be 1. If I have tail head, then the value would be 2. It's the second toss that gives me a head. If I get tail head, then the value of the random variable is 3. I need 3 tosses before I see a head, and so on. Okay? So what is the expected number of tosses that I need to make before I actually see a head? So let's try to see. The formula tells us that this is going to be the sum over all possible outcomes. And in this case, the outcomes are going to be all possible sequences of bit strings. So there are lots of them. And there are infinitely many, actually. Because we don't say how many times we're going to toss the coin. We toss until we get a head. So there are infinitely many. Possible outcomes. Okay, in particular, sort of the possible outcomes are actually can be taken to be the natural numbers from, greater or equal than 1. Just for this specific example. Okay, so the probability that I get a head the first time around is what? It's a half. So this thing would be something like, let's see what the outcome is going to be. Sort of, so I can rewrite this as saying, the S's are the natural numbers. So probability that I get it after 1 is a half. Plus the probability that I get it the second time round. So it's so I get 2 as my value of the random variable, but it's 1/4, isn't it? That's the probability of tail head. Okay, in general, the probability that I get to the third time round is going to be 1/8 because it's only tail head. So the formula is, okay, S times 1 over 2 to the power s. Because s is a natural number going from 1 to 3n, and that's an infinite sum. Now, I'm not asking you to calculate this this thing. It's actually 2. So the expected number of tosses that you need to make before for getting ahead the first time round is 2. And again, this sort of makes perfect sense. Forget about these infinite sums. I mean, they're not something you're expected to be able to compute. Not in general, at least. But let's focus on the intuition. Okay, so every time I toss a coin, the probability that I get ahead is a half. So if I toss it twice, I would expect, on average, to get 1 head and 1 tail. That's why, on average, I need to toss my coin twice before I get ahead. Note, this is just an average computation. You might be unlucky, you're going to get any. But that starts being fairly unlikely if you repeat this experiment many times. Since each time you toss the coin, you have a probability of 0.5, a half of getting ahead. If you toss it twice, you expect to see 1 out of 2 of the tosses to be ahead, on average. Okay, so this definition, again, sort of links nicely with intuition. And that's one of the reasons why people have put it together a while back. Okay, so let's get back to a simpler example. Let's again consider my random variable that counts number of heads in, I said before, 1,000 coin tosses, where the coin is fair. Okay, if you use the formula for the expectation, you would have to sum over all possible outcomes, and there are 2 to the power of 1,000. A lot. However, I claimed before that you don't need to. There is a property of expectation that tells you how to compute this value without considering all of the possible outcomes. But by doing what we computer scientists love and do all the time, namely divide and conquer. It's a very useful algorithmic technique that dates back to the Roman Emperor Augustus, at least, where he needed to rule a huge empire. So what he did was to divide it up into sub-empires, sufficiently small sub-empires, and let somebody rule in his place for each one of the sub-empires, and then collect them all. Okay, so what does this mean in this specific setting? Let's see. This means, yes. Sorry, I'm being asked to draw the blinds a little bit more so that we are in full cinema mode. You know, the sun is out here in Reykjavik, rejoicing, but this does not completely fit with a nice experience here in the lecture room. So let me introduce to you 2 properties of expectations over random variables. Suppose somebody gives you 2 random variables, x1 and x2, that are over the same sample space. Out of these two random variables, you can define a third random variable, which is the sum of the two. Now, what does this mean? Scratch pad. So I have a random variable x1 from my sample space S to the collection of real numbers. Note, this is nothing but a function from S to real numbers. I have another random variable x2 that again goes from the same sample space S to real numbers. Now, what is the random variable x1 plus x2? Well, again, that should be a function from S to the real numbers. And what function is this? Well, it's a function that does the following. Give me an S, a possible outcome. I'll give you the sum of the possible of x1s and x2s. So if x1s is the payment that you get every time outcome S occurs, and x2s is the payment that you get every time outcome S occurs according to x2, then x1 plus x2 gives you the sum of the two payments. So if x1 counts the number of heads in the first toss of two coins, and x2, for instance, counts the number of heads in the second toss of two coins, x1 plus x2 counts what? So x1 takes a string of heads and tails of length 2, and it tells you 0 if you have a tail in the first position, 1 if you have a head in the first position. And x2 does the same for the second position. So x1 plus x2 counts the number of heads in the string. Okay, now, you know what the magic property is going to be, which has got nothing to do with magic, of course, is that the expectation of the random variable x1 plus x2 is nothing but the expectation of the random variable x1 plus the expectation of the random variable x2. And this is happiness. Why? Well, for two reasons. First of all, because the proof of this equality is easy peasy. It's easy. And second, because you've already seen a similar property somewhere else. Where? Linearity of matrix transformations. That's one of the two properties of linearity. And actually, if I flash again the slide and you look at the second property of expectation, that's the other property of linearity. So expectation is a linear function. You know, you thought you had got rid of linear functions. Well, not quite. They come back with a vengeance. And you will see how useful these properties are when you need to compute expectations of apparently very complicated random variables. So do you want to see why this property is true? Well, I mean, the yes is not very convincing, but it's resounding. And anyway, I really need to show this to you because it's actually easy. So let's see. All we need to do is to use the definition of expectation. So what is the expectation of x1 plus x2? Well, it's the sum over all possible outcomes in our sample space of what? of the probability of getting that outcome times the value of the random variable x1 plus x2 for that outcome. That's just the definition of expectation. Okay, so you have a set of possible outcomes. For each possible outcome, you have a payoff. The amount of money, say, if you want to talk about money, that you're going to get when that outcome occurs. The value of that outcome. So you want to compute the weighted average, all you need to do is to take the sum of the probability of each outcome times the value of the outcome. That will give you the average payoff that you're going to get. But now, what is this? Well, all we need to do is to look at the definition of the sum of two random variables. Well, this is nothing but the probability of seeing S times what? x1, the value that x1 assigns to S, plus the value that x2 assigns to S. But hey, now I can distribute, isn't it? So this is actually the sum of what? PS times x1s plus PS times x2s. Okay, so all I'm doing is distributing the multiplication over the sum. And now we are basically in business. Why? Because this thing is actually two sums in one. I can take all of the contributions from x1 and all of the contributions from x2 for each one of the outcomes. And I sum them together. Plus what? All of the contributions from x2. And I sum them together. But hey, what is this? The blue circle thing. And what is this? The green circle thing. What is the blue thing? It's the expectation of the variable x1. And what is the green stuff? The expectation of the variable x2. Which is what I was claiming was true. Namely, the expectation of the sum of two random variables is nothing but the expectation, the sum of the expectations of the individual random variables. Which tells us how we can compute expectation of sums of random variables recursively. You just compute them individually, and then you sum all the values. Now you may say, why is this useful? Let me give you 3 reasons why this is useful. And these 3 reasons are 3 examples. So, ladies and gentlemen of the jury, exhibit number 1 to show you that this is useful. Let's go back to our nasty motivating example. Now, S is the collection of the results of 1,000 coin flips. X is the random variable that counts the number of heads. Now, what is the expectation of X equal to? And I don't want to compute the sum, the weighted average, over 2 to the power of 1,000 strings. Allow me to be lazy. And even if I weren't lazy, allow me not to be crazy, because I want to do something for the rest of my life, perhaps, apart from computing this average, which I will never finish anyway. So, let me define the following random variables for x1, x2, x3, x4, boom, 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 x to the 1,000. These are all random variables from the set of all outcomes to the real numbers. And now, how do I define them? I define them as follows. Xi is really going of some outcome S, sorry. It's going to be 1 if the ith symbol in S is ahead, and 0 otherwise. So you get, as an input, a sequence of 1,000 coin flips, the result of a sequence of 1,000 coin flips. And you only focus on one of the flips. And you count whether that's a head or a tail. Okay? So you take 1,000 coin flips, the results of 1,000 coin flips, but you only look at one of them. And you say, okay, my random variable xi is going to give me 1 if that's a head. Otherwise, it's going to give me 0. So the random variable xi counts the number of heads that you got in the ith flip. Now, what is the expected value of the variable, the random variable xi? Okay, with probability a half, you get a 1. With probability a half, you get 0. So the expected value of xi is, let's calculate. So the expected value of xi is, with probability a half, I get the value 1, plus with probability a half, I get the value 0. So it's a half, which is nothing but the weighted average of 1 and 0, where the weight is a half. It makes perfect sense, doesn't it? Because if you toss a coin and you get 1 kroner every time, sorry, this is small amounts, but anyway, it's just for, by way of example, you get 1 euro or $1 every time you get a 1, a head, and you get nothing every time you get a tail, when on average you expect 50 cents. Okay, because you only get 1 euro half of the time. So on average, you get half of the number of tosses. That's your expected gain. Now, why does this help me? Well, because actually the random variable x is nothing but x1 plus x2 plus x3 plus x 1000. Why? Because x counts the number of heads that I got in my 1000 flips. And this is nothing but the number of heads I got the first time, plus the number of heads I got the second time, plus the number of heads I got all of the other times. But since expectation is linear, I know that this is actually the sum of the individual expectations. The sum from 1 to 1000. But what is this? It's 1000 times a half. Because all of the random variables that I'm summing have expectation a half. So it's 500. Which again makes perfect sense. Why? Because half of the times I'm expected to get heads. Because the coin is fair. Yes. Yeah. Okay, so the question is, what if the coin was biased? So for instance, I get a head with probability 2/3, say, and the tail with probability 1/3. In that case, the expectation of the random variable xi would be 2/3, because it's 2/3 times 1 plus 1/3 times 0. And then all you would need to do is just to run the same calculation here, but instead of 1000 times a half, you would get 1000 times 2/3. Excellent question. Thank you. So the calculation really, the general method doesn't have anything to do with the fact that the coin is fair or not. It's everything to do with the fact that we are dealing with expectation which is linear. Okay, exhibit number 2. Are you happy with this calculation? Excellent. Let me give you another exhibit now of the usefulness of linearity of expectation. And this is yet another opportunity for us to refresh our knowledge of Bernoulli trials. Suppose I have a random variable, x, that counts the number of successes in a Bernoulli trial of length n with probability p. That's the probability of success. So in other words, you have a Bernoulli experiment, you repeat it n times, and you want to know what is the average number of successes that I expect to encounter. Now, if n is big, I mean, you have a fair amount of possibilities, 2 to the n possibilities. So the formula that we used for calculating the expectation ends up being a big sum of stuff. But you know, we can use linearity to simplify this substantially. Why? Because, okay, sort of this random variable takes as input a trial of length n. So where Ti is the result of the ith trial. And this result could be success or failure. Zero or one, heads or tails. I think we've seen this before, haven't we? In fact, fairly recently. Because the example that I gave you before was a Bernoulli trial where the experiment was tossing a coin, a fair coin. And with the modification that your colleagues suggested, tossing an unfair coin, where the probability of getting heads is P. So in fact, the second exhibit is very close to the first one, actually, but that's another matter. Okay, so how can we go about calculating the expected number of successes? Well, we do exactly the same that we did before. We define random variables, xi, where I ranges from 1 to n. And what is xi of t1, tn? Well, we only look at ti, at the ith, the result of the ith experiment, and we say 1 if ti is a success, and 0 if ti is a failure. Now, what is the expectation of the random variable xi? Well, we have 1 with probability p, which is the probability of success, plus 0 with probability 1 minus p. So that's p. Note, this is in complete agreement with what we did before in the case of tossing a coin. Absolutely. Your colleague is saying, hey, but now I know what the expectation of x is. Because x is nothing but x1 plus x2 plus x3 plus xn. Why? Because each one of the random variables counts success in one of the trials. X counts success in all of the trials, so it's the sum of them all. And this expectation is nothing but n times the expectation of each one of the xi's, which is p. N times p. So before, our n was 1,000 for the coin tossing trial. Our p was a half. That's why we got 500. In the modification suggested by Sigrun, again, n was 1,000 and p was 2/3. That's why we got 1,000 times 2/3. And again, a complicated looking situation was reduced to the scenario in which we just simplify by looking at one of the much simpler random variables. The simpler random variables sum together give us the complicated random variable, and we can compute the expected value of the complicated thing by a simple manipulation of the expected value of the components. Divide and conquer. It's basically exploiting the power of a recursion, of a recursive calculation. Okay, so let me give you another exhibit on our way out. And this is sort of a fun problem that you see in all kinds of probability texts, which is called the hat check problem. That's an R. So how does this work? Suppose that you were at a party, and this party is held by posh people, And at the entrance, you leave your hat. We're all supposed to wear hats in this in this problem. So you leave your hat to somebody who acts as a receptionist. Now, this somebody has the following policy for returning the hats. When you go, he chooses one of the hats at random, and he gives it to you. Now, the question is, on average, how many people get their hat back? This looks like a very complicated problem. In fact, if you use linearity of expectations, it isn't. Because why is that? Okay, so suppose that I have, what is the probability there are hen hats? Now, let's look at the random variable that only focuses on one of you. Goodney, say. What is the probability that Goodney, out of hen hats, gets his one back? It's 1 over n. So if you look at the random variable x Goodney, so there is a sequence of hats of length n, h1, hn, and now Goodney is somewhere in here. He is the ith guy. This is defined to be 1 if hi is sort of Goodney, and it's 0 otherwise. Now, what is the expected value of this random variable? Well, let me call it xi now, so that I don't have to write this name again and misspell it a million times. Okay, well, the probability that he gets the right hat is 1 over n times 1, because he got the right hat, plus 0 times the rest. But it's 1 over n. Okay, so this is the probability that, so this is the random variable that tells you if the ith guy, in particular Goodney in our example, gets his hat back. And this is 1 over n. But now there are n guys. The number of guys who get the right hat is the sum of all of the individual expectations. So it's just n times the probability of the expectation of the hat check is n times 1 over n, which is 1. On average, only one of the guys gets his hat back, the right one. And I encourage you to try the specific calculations using the formula for expectation for the case of 2 people and 3 people. For 4 people, don't do it because it's already 4 factorial possibilities. And sort of, well, it's a 24 long sum, so that you don't want to do it. But for 2 and 3, do the calculation using the standard, sort of the formula, the summation formula for the expectation, and you will see that you get 1 in each case. In fact, it's always 1. For 1,000 people, 1 billion people, all the inhabitants of the earth, it's the expected value is 1. And this corresponds to take, okay, you take n numbers, you permute them in an arbitrary order. What is the expected number of what is called a fixed point? A number that has stayed where it was before you permuted it. Well, the expected number is 1. Okay, and since it's 1:55, it's time to call this a day. So we meet again next Tuesday for the 23rd session of the course. And if there is something that you would really like to see covered in the last week of the course, once more for my enlightenment and our joint enlightenment, just mark it on Piazza in the thread, which was started a while back. Oh, God. Sorry.